Hello, everyone. A very warm welcome to all of you from the Astronomical League of the Philippines. I am Jet Aguilar, and I will be your host for today's webinar. Thank you so much for joining us for our third online talk for our ALP Astronomy Experts Speaker Series of 2023. I am happy to see a lot of registrants attending, not only from the Philippines, but also from all other countries as well. It has been a year since the James Webb Space Telescope launched into space on Christmas Day of 2021. During its first year, this innovative observatory has already made revolutionary advances across astronomy with its infrared capability and high sensitivity. We are deeply honored and very fortunate to have with us today one of the interdisciplinary scientists who had been directly involved with the James Webb Space Telescope and who will share with us not only her personal insights about the new space telescope, but also the amazing results of its first year of operations. Ms. Imelda Johnson will be introducing our distinguished speaker later. For those who were not able to register, but would still want to watch this webinar, we are currently live streaming on Facebook at the Facebook page of the Philippine Astronomy Forum. Before we start, kindly allow me to explain some rules for this webinar to help us make this an enjoyable learning experience for everyone. Please listen and do your best to give your undivided attention to our speaker. There will be a short question and answer session at the end of the lecture. You may type in your questions under the Q&A tab found in your Zoom interface at any point during the presentation. We will do our best to read and answer your questions live after the lecture or via the Q&A tab. We would like to remind everyone that the contents presented at this webinar will remain as the individual property of the lecturer and the photographers in the presentation. We will also be distributing certificates of attendance via email to all registered attendees who will be present with us throughout the webinar. So please use the name you have written in your registration forms to help us facilitate this process. Let us all enjoy this talk and have fun learning. Here is the program flow for today's webinar. I would like to turn you over now to Mr. James T, the President of the Astronomical League of the Philippines, to give his welcome remarks.
Good morning to our viewers in the Philippines, as well as good evening to our guests in the United States and Europe. My name is James T, President of the Astronomical League of the Philippines. And on behalf of the organization, I would like to welcome you to our Astronomy Expert Speakers Series 2023. This webinar is a part of Astronomical League of the Philippines International Astronomy Educational Outreach Program. Our goal is to bring renowned experts and scientists to the Filipino people as well as the rest of the world. That's why the webinar is being offered for free to the general public. I would like to take this opportunity also to thank our ALT members who have been instrumental in putting up this program altogether, especially Imelda Johnson, Edwin Aguirre, Dr. Jet Aguilar, Jun Lau, KCT, Andrew Arenchan, and Peter Tobalina. So this will be in overall, the speaker series we have, this will be our 12th lecture and the third one for 2023. Our speaker for today is Dr. Heidi Hammel, interdisciplinary scientist of James Webb Space Telescope, as well as VP of Science, Association of Universities for Research in Astronomy, as well as the president of the Planetary Society. We have more distinguished speakers lined up for the coming months, so please stay tuned. And please do not forget to register in advance for this future webinar. Thank you very much. And now I would like to turn over the program to Imelda Johnson, who will introduce our guest speaker for today.
Good morning, everybody, all our friends in the Philippines, and good evening to all our friends here in the United States. Today's speaker need no further introduction to planetary scientists and to all the women in astronomy whom she had inspired through the years. Dr. Heidi Hammel became a media sensation 29 years ago when, as a very young astronomer, she courageously interrupted a NASA STSCI press conference to share with the world the first images of comet Shoemaker-Levy 9's impact on Jupiter, taken using the Hubble Space Telescope, where she led the HST team that studied the planet's atmospheric response to the collision. Dr. Hammel is a planetary astronomer who has used some of the most impressive telescopes available to astronomers, like Gemini, Hubble, Keck, Spitzer, and many others, to study our solar system's outer planets, their rings, and their moons. Currently, she's an interdisciplinary scientist for the James Webb Space Telescope and focuses on planetary systems and the origin of life. Her latest research involves studies of Uranus and Neptune using the Hubble Space Telescope and other Earth-based observatories. She is an expert on these distant planets, and she was a member of the imaging science team for the Voyager 2 encounter with Neptune in 1989. Dr. Hammel has been part of a team working to launch a mission to the outer solar system sometime in the next decade. She received her undergraduate degree from the Massachusetts Institute of Technology, MIT, in 1982, and her Ph.D. in physics and astronomy from the University of Hawaii in 1988. After a postdoctoral position at NASA's Jet Propulsion Laboratory in Pasadena, California, Dr. Hammel returned to MIT, where she spent nearly 9 years as a principal research scientist in the Department of Earth, Atmospheric, and Planetary Sciences. In 1996, she was awarded the Urey Prize, and in 2020, the Mazursky Award by the American Astronomical Society for her outstanding achievement in planetary science. She joined the Space Telescope Science Institute in 1998 and retains a position there as a senior research scientist. She now serves as the Vice President for Science at the Association of Universities for Research in Astronomy. Dr. Hammel is an award-winning communicator of science. She is especially skilled at translating complex science concepts into easy-to-understand language for the general audiences. She also has a strong belief in the value of public education. Dr. Hammel won the American Astronomical Society's Division of Planetary Science 2002 Sagan Medal for her outstanding communication by an active planetary scientist to the general public, as well as a Public Understanding of Science Award from the Exploratorium in San Francisco, California. Her biography, Beyond Jupiter, the story of planetary astronomer Heidi Hammel, has been published by the National Academy of Sciences as part of the series Women's Adventures in Science. She was also profiled in Newsweek magazine in 2007, and in 1996, the International Astronomical Union named asteroid 1981 EC20 as 3530 Hammel in her honor. Friends, let us welcome Dr. Heidi Hammel.
Thank you so much for that lovely welcome. I'm really honored to be here and to be able to share with you tonight some of the highlights from the first year of science with the James Webb Space Telescope. So let me pull up my screen because I have many, many pictures to show you. And let us share this and start it running. And I hope if you all give me a thumbs up so I can see from the panelists that all is working well. Fantastic. So I'm going to start first with some physics because I want us all to understand the importance of spectroscopy, because that is the superpower of the James Webb Space Telescope. We will talk about the beautiful images as well, like you can see on the screen, or you can see behind me in my picture. But I'm really going to talk about spectroscopy, because that is some of the most amazing things coming from James Webb Space Telescope. So let's go all the way back to Isaac Newton. And remember how Isaac Newton put a prism in a hole in the wall and took the white sunlight, and the prism spread it out into the rainbow of colors that we call the visible spectrum, from red to indigo. But what we all know is that light doesn't just stop at red or at blue or indigo. Light continues on at wavelengths that are longer than our eyes can see in the case of the red, or shorter than our eyes can see in the case of the blue. And all of these have names, and I'm sure you know many of these names. The very longest wavelengths of light are radio wavelengths of light. Some of the very shortest wavelengths of light are X-ray, which, you know, if you've ever had a broken bone, you've had images taken in X-ray light to see that bone. I'm clutching my wrist because I had a broken wrist and had many X-rays of that wrist. But there are many other kinds of light. And what we're very interested in for James Webb Space Telescope is light that is longer than our eyes can see. And that is the near infrared and the mid infrared. And I'm going to tell you why we want those colors. But let me tell you some of the reasons we care. First of all, the universe emits light at all of these wavelengths. It doesn't just emit light at visible wavelengths. And so we astronomers, we want telescopes that will cover that full electromagnetic spectrum. That's what we call that full spectrum, the full rainbow, from the gamma rays all the way out to the radio wavelengths. And we have, in fact, built these telescopes. Hubble is a telescope that focuses primarily on ultraviolet and visible and a little bit of the near infrared. And so lots of beautiful pictures from Hubble. JWST picks up where Hubble is leaving off and extends much further into the infrared. And you can see from those pictures, we have other telescopes that do other things. So why was James Webb Space Telescope decided to be an infrared telescope? There's a couple of reasons. One is that infrared light reveals hidden things. This is a visible wavelength image of the sky with a constellation that's familiar to many of us, the constellation of Orion, the 3 stars making his belt, the shoulders, the knees, and then the sword hanging from the belt. But this is a visible wavelength image. And if you had infrared eyes, if you were, say, a mosquito, which can actually see infrared wavelength, and you were a mosquito buzzing around outside in the winter and you looked up and you saw Orion, it wouldn't look like that. It would look like this. That is what Orion looks like in infrared light, because Orion is a huge cloud of dust, and that dust obscures a lot of the light at visible wavelengths. That's why it's dark. There are some openings in this dusty cloud. One of them, a very famous one, if you can see my cursor, can you see my cursor moving on the screen? Yeah. Right in there in the sword that's hanging from the belt, that's a little opening into this massive dust cloud. And you can see how bright it is here, but all the rest of this dust, we don't see at visible wavelengths. So the infrared light reveals new things to us. But now I'm going to switch gears a little bit, because I'm going to talk about the other reason we want to look at the infrared. And to do that, I have to introduce the concept of spectroscopy, because spectroscopy is JWST's superpower, as I said. So if we look at the visible wavelength of light, and this is true actually not just visible, all of the electromagnetic spectrum, some materials, depending on their pressure and temperature, they can absorb colors in the spectrum. It's a quantum mechanical effect. It has to do with how electrons are shifting around in the shells around the nucleus, but they basically can take light out at characteristic wavelengths. And in other conditions, other temperatures and other pressures, sometimes those quantum mechanical effects will put light back into the spectrum. You actually have extra light at some wavelengths. And these characteristic patterns of light are what we call the spectra. We often don't show it as I'm showing it here with the rainbow and the black lines where there's missing light and the white lines where there's extra light. We show it as kind of a graph of things, and that's what we call a spectrum. But it's linked to the light, as I show above. So where things are added to the spectrum, you have something going high. And when things are taken out of the spectrum, it dips down. And we use words like absorption. That's where things are absorbing light, they're making it go down, or emission. That's where that extra light is added. So I might slip up and use words like absorption line or emission line, but that's what I'm talking about, characteristic fingerprints. So let me show you an example from the Hubble Space Telescope. Here's a beautiful image of Eta Carina. This is a very, very massive star that is exploding material out, as you can see, into this interesting bilobe structure. But the science doesn't only come from this image. We put a slit, which is the equivalent of a prism, onto this exploding star, and we spread that light out. And what you see there is a pattern of emission lines, bright additions to the spectrum. And because of their location as a function of wavelength, we can clearly identify what is in this exploding star. We see helium, argon, iron, nickel. You can even see that some of the lines are tilted a little bit. That tells you things about the dynamics that are taking place. So from a spectrum of this exploding star, we can learn its composition, we can learn its temperature, we can determine the pressure of the materials that are doing this emission in this case. We can also sense the dynamics. So this is really how we do science of objects in outer space where we can't visit them. That's how we know the temperatures. It's how we know what stars are made of and what nebulae are made of. And there's another very important aspect of spectroscopy for studying our universe, and that is something called cosmological redshift. So if you take a spectrum of a nearby star, you see characteristic pattern of lines that we know are from hydrogen. And they're labeled in this graph, alpha, beta, gamma, delta, epsilon. There's other lines as well. But if you look at a nearby galaxy, which is composed of stars who have a lot of hydrogen in them, if you look carefully, you'll notice they're shifted just a teeny bit to the red. And if you look at a very distant galaxy, now that shift to the red is more evident. But if you look at the very most distant galaxies that Hubble has had access to in the Hubble Deep Field, which probes to the edge of the universe, those shifted lines go way over into the infrared. And so when we were designing the next generation space telescope to follow Hubble, we wanted to use that telescope to look for the most distant galaxies visible in the universe. And you can see in this chart that these characteristic lines that we're looking for from those most distant galaxies, they are shifted out of the visible, out into the infrared part of the spectrum. And so that is why we built the James Webb Space Telescope, why it is an infrared tuned telescope. And the ability to look in the infrared drove all of the design characteristics. So if I compare JWST with Hubble, you can see that they're kind of overall the same scale, but the primary mirror of JWST you can see it sort of video. The mirror of JWST is not silver. It's coated in gold, pure gold, a very thin, few molecules thick layer of gold. And we didn't do that just to make it look pretty. We did that because gold is an extremely effective infrared reflector. Silver is not. And that is why we do not make this a silver mirror like Hubble. And so that's why it's a gold mirror. The fact that we're looking in the infrared is also why we don't have a tube like Hubble has, a tube enclosing it, because the tube radiates warmth, and warmth is another word for infrared light. Infrared light is heat. Heat is infrared light. They are the same thing. And so the tube is a warm thing, and it's so warm that the signal from the tube would swamp the warmth from the distant galaxies at the edge of the universe. So no tube, it's not there. Telescope is sitting out in outer space. And there's challenges associated with that you may have heard about, like micrometeoroid impacts. We can talk about that later. There's also this very large sun shield. And the reason we have that sun shield is to protect this telescope from the warmth from the sun, the earth, and the moon. All of those are being shadowed by that very large sun shield. And all of these things are to allow us to make incredible infrared observations of the most distant galaxies in the universe. And that is, in fact, the key science from James Webb. The number one reason it was built is to find the light from the first galaxies that ever formed in our universe. But because it is such a powerful telescope and can see all the way to the first galaxies, it can see all the galaxies in between us here and there. And therefore, we also have a science theme devoted to studying how galaxies assemble and evolve over cosmic time. A third science theme is looking within these galaxies in our local neighborhood to study how stars are born and how planetary systems form in stellar nurseries. And the fourth science theme for JWST is planetary systems and the origins of life. And as was mentioned in the introduction, this is the science theme that I have been focused on as an interdisciplinary scientist for JWST. My particular focus has been our planetary system, the solar system, and using this telescope to make many different kinds of observations within our solar system. And so we'll talk about that. But now, let us go back more than a year, all the way to Christmas Day of 2021. That was the day that we launched JWST after a very, very long development. When I say long, I will share with you that I started working on this project more than 20 years ago. 20 years ago was when I was officially invited to be an interdisciplinary scientist for the program. But I had actually been working on this program for quite a few years before that as well. And so those of us who have been with this program for this whole 2 decades of development and work and waiting, this moment on Christmas morning, when we put our precious telescope on the top of an Ariane 5 rocket and lit the fuse of the rocket to send this telescope to space, was one of the scariest moments. It's rocket science is never guaranteed. So I'm going to show you now a video from French Guiana, where the rocket was launched. This was a French rocket provided by the European Space Agency, who is one of our key partners with NASA and the Canadian Space Agency in building JWST. And so it's launched on a French rocket. So you will hear the countdown in French, and then you will see the rocket launching. And then there's some people I'm going to talk about when you see them. So here we go. Rocket launch. Merry Christmas.
6, 5, 4, 3, 2, unité,
Nicolage liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
That woman hyperventilating, that was all of us. All of us were.
The clouds, 20 seconds into the flight, good pitch program recorded.
So the Ariane rocket put us on an absolutely perfect orbit, a perfect trajectory to head to the place where Webb will be operating. That's the Sun-Earth Lagrange 2 point. There was a camera inside the Ariane rocket fairing that allowed us to see the detachment of JWST from the rocket fairing. And you can then see the telescope moving away. It's all folded up, so it doesn't look like the telescope yet. But you can see the little retro rockets firing. And so there you see it going. There's no sound for this one. You see the little blue flashes in that ring. Those are little rocket firings that are helping to push this on the right trajectory. Telescopes all folded up, but right here you see a solar panel deploying. And so that is how we start to have the power for the deployment sequence that is to come. So launched there on Christmas Day 2021, and you can see in this illustration that the telescope is actually literally folded. The mirror itself is folded up. Two wings have been folded around, and the sun shield is all folded up. And so the next month after the launch was a complex series of deployments and unfolding. And it took a full month for all that to happen. And this was a very white knuckle time, nerve-wracking time. There were 100 or more single point failures that if the thing didn't deploy or move, we didn't have a telescope, but all of it worked perfectly. And so by the time a month had gone by, our telescope had completely unfolded into its operational configuration and was then put into orbit around the Lagrange 2 point. So let me do a little cartoon for you of what Lagrange 2 is. If you draw a line from the sun to our Earth and then keep going in a straight line for another 1.5 million kilometers, about 1 million miles, there's a point there called L2, Lagrange 2. It's a gravitationally stable point. And we put spacecraft at these places. We don't put them exactly at L2. We put them in a tiny orbit around L2 because it requires very little, relatively little fuel to keep it into that gravitationally stable point. And so it's a great place to put a spacecraft. The James Webb Space Telescope was not the first telescope to go to L2. The WMAP telescope was there. There were other telescopes there as well. It's a big space, right? So they don't hit one another. So that is where we sent this telescope. So remember that the farthest humans have ever been from our planet Earth is the moon. L2 is about 4 times further than the moon. So unlike Hubble, which was serviced by astronauts 5 times, there's no servicing of of JWST, sorry. You can't service JWST. It's just too far away. We don't have the technology. So that's where we put JWST. And I remember the sun shield I mentioned. I wanted to show you this picture because this is not what JWST looks like at L2. Because notice the sun shield in this configuration is not blocking the sun or the Earth or the moon. JWST is always in this configuration at L2, and it travels around the sun, always in the straight line, sun, Earth, JWST. And it's always in this configuration. And the telescope itself, the mirror part, can move around and tilt a little bit. So there's sort of a cone that we can look at things, but we can never look back inward, and we can never look straight outward. So that's what we call our field of regard, in this sort of this circle in the sky that's set up by this geometry with the sun shield. Once we got to L2, after a month, we spent then almost half a year getting the telescope ready to do the science. This is a little chart that we developed I'm not going to read all those words. There is a blog on the Planetary Society's website where I describe all of this process and go through this diagram in more detail. So if you want to learn more about the commissioning phases of the telescope, you can read that blog, and it talks about what we were planning to do, and everything went exactly according to plan. The green section, the first 3 months, were based on focusing the mirrors of the telescope. There are 18 different segments. They all had to focus as one, but that was done. The rest of the time, in the sort of the lavender color, that was the commissioning of the instruments, making sure the cameras and the spectrographs were all properly functioning, starting to do the calibration work we need to use them effectively. And so that was the first 6 months was all of this work. That brought us to July, and that was when we actually started doing science. So it's March. We're not to July yet, so we actually have not yet finished a first full year of science with JWST. So I'm going to show you what we've been doing in sort of the first 6 to 8 months, but we're not even done with our first year of science, and we have amazing data. The last preparatory slide, I wanted to show you the evolution of our ability to have infrared space telescopes. JWST is not the first. We've actually had others. Here's an image of a cluster of a small group of stars with the WISE telescope, which was a space telescope. Then the Spitzer Space Telescope came along, much better than WISE. You can see how crisp those stars are starting to be. And you now start to see hints of dusty material in this particular image. But now let me show you the same field with our perfectly focused JWST. And that's what we see. And so now you start to see why we were getting excited. We saw our telescope so beautifully focused and just amazing quality of detail in the infrared, a whole new world, a whole new universe opening up to us with JWST. So let's talk about the first set of images. I'm sure you've seen these images, so I just want to share a little bit about what I think is really exciting about them. This was our first deep field. It's a picture of a cluster of galaxies. The objects that you see that have these spikes that coming off of them, those are what we call diffraction spikes. Those are generally stars. You can see a star here and a star here, this bright star here. But these other objects that don't have that, those fuzzy objects, those are actually galaxies. And there's many galaxies in this cluster of some very big, large galaxies. And a galaxy is a collection of billions of stars, sometimes at the largest galaxies, hundreds of billions of stars. And there are all these white fuzzy galaxies in this cluster of galaxies. And there's so much mass in this cluster that it is actually distorting space-time. Einstein predicted that. He said massive objects will bend space. And if you look carefully, let me zoom in a little bit here, you can see arcs. You can see sort of a pattern of red streaky things. Those are actually distant galaxies that are being distorted by this space-time. And I'm zooming in on the background here because every piece of this image is like a Hubble deep field. You know, with a few stars you see, but everything else you see here is galaxies. And some of these, the little tiniest, faintest ones, those are, in this image at that time, some of the most distant galaxies ever seen. And how do we know that? Remember what I talked about in the beginning, the spectroscopy? First, I'll show you a Hubble image. Here's a Hubble image of this field. You notice how it's hard to see a lot of those galaxies, but when we turn on the infrared cameras of JWST, they pop out. So we went, the scientists who focus on distant galaxies, they went through all of those little tiny dots, the ones that you could barely see in this image, and they picked out the ones that were the reddest ones, and they did follow-up spectroscopy of them. And look what you see. This is a sequence of galaxies that are redder and redder. And here's these patterns of the spectra, hydrogen and oxygen. And as you look at more distant galaxies, look what happens. The hydrogen and oxygen is shifted to the red. More distant galaxies further, more distant galaxies further. This is exactly what I explained to you about that cosmological redshift, except this is real data. This is actual molecules of hydrogen and oxygen in the most distant galaxies in the universe, that we are seeing the signature of those molecules for galaxies at the edge of the universe. I mean, to me, that is like a mind-blowing thing. But that's what JWST was designed to do. And by golly, that is what it's doing. This was actually a short exposure. We called it a deep field because it was it was 12.5 minutes. We have since the teams who are doing this deep galactic surveys, they have now done 20-hour exposures and then another 20 hours. So there's so much deep science going to be done. It's doing exactly what we wanted to do. It is probing to the edge of cosmic time itself. So very exciting. We do look at galaxies nearby. As I told you, we can see galaxies here, galaxies far. This is a very photogenic cluster of galaxies called Stephan's Quintet. There are 5 galaxies in the image, but if you look closely at these images, you'll notice that one of the galaxies is actually not like the others. You can zoom in on this galaxy that's on the left there, and you see that it is speckled with tiny stars. But if you look at the galaxies to the right, they're not speckled, they're very smooth. The reason is that galaxy to the left is a foreground galaxy that is photobombing the cluster. The cluster is much, 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 much further. Here we are swinging off to the side so that you can see the deep field aspect of this image of the foreground here. So we've got sort of 3 levels of galaxies here. We've got a really close one, we've got really distant ones, and super far ones. I showed this because this is a far infrared image with JWST. Those galaxies look a little different. They don't look quite as dramatic as the other images. You're kind of looking at the skeleton, if you will. You're looking at the dusty lanes where stars are being born here in the far infrared. And I particularly wanted to focus on the one at the top. You'll notice that there's what you do see is diffraction spikes up here. And so remember, I told you that that was mostly stars that had diffraction spikes. But what you've got here in the core of this particular galaxy in Stephan's Quintet is you have what we call an active galactic nucleus. It harbors a black hole in the core of that galaxy. And material is pouring onto that, being pulled into it. And there's a disk of material that is being swirling around the black hole. We don't see the black hole. We see the black hole's effect on this disk of material that is pouring into it. And so using the spectroscopic capability of JWST, we put a spectrograph right on the core and also on the outskirts. And if you look on the outskirts of this disk of material, you see iron and argon and neon and sulfur. This is all material that's being shredded by the power of this black hole. But really interesting to me is that when you look at the actual core, you see an absorption here. You see absorption from silicate. This is the dusty disk that is surrounding the black hole. You're seeing the spectral signature of the silicates in the dust in that powerful disk around this active galactic nucleus. So again, this is the science we do with spectroscopy. The birth of stars, this is a sort of now an iconic image. You can see it on the wall behind me. We call it the cosmic cliffs. What the cosmic cliffs actually are the edge of a cosmic bubble. It's a very large bubble. That blueness is the open space in the bubble. And this brown material you see is sort of the material that the young stars are blowing this bubble into a dusty cloud. And when the dusty cloud gets compressed by the young stars that are pushing it downward, new stars get born in that dust. And the reason that we astronomers are so excited about this particular image is that it's revealing many, many details on star formation processes within that molecular cloud. I saw an hour-long talk about this one image, an hour, pulling apart all kinds of details embedded in the dust, that brown dust that you see there. There are areas where newborn stars are poking out. We'll take a look at longer wavelengths now, also taken with JWST. At these even longer wavelengths, much of this dust disappears at the longer wavelengths. We're seeing right through it. And so if we do that, it will zoom in on this piece at longer wavelengths. You immediately saw how much of that you can see through the dust. But what you really find is areas like this, if you can see my cursor, where brand new stars are breaking free of the cocoons of dust in which they were made. And over here, you see what looks like a red streak. This is newborn stars that are just starting to push through the dust. Up above it, you can see what look like jets shooting out. If you look very closely, there's signatures of jets all throughout this dusty region. Those jets are from young stars that are just being born. So tremendous wealth of data in these beautiful images. We not only watch stars being born, we watch the stars at the end of their life. One of the first images released was this. This is a picture from Hubble of something called the Southern Ring Nebula. And with JWST, we can get far more detail than Hubble could get. So let me fade to the JWST image. And you see how much more structure is evident in this material around this star that is ejecting material. This is a near infrared wavelength. Let me zoom into the center here, because there was actually a little surprise embedded in these data. If you look at this, you see the star right in the middle, and you're like, oh, that must be the star that's ejecting this material, right? Actually, no. When you look with the long wavelengths of JWST, watch what happens right there in the center. Put my cursor there if you can see it. Watch what happens. Another star pops out, a red star. That star is the star that is ejecting this material, and it's invisible at the shorter wavelengths because it's encased in the dust shell that hasn't expanded out yet into the beautiful nebula that you see. It will at some point in the future. All of the structure here, you'll notice it's not spherically symmetric. When scientists who study these things have modeled this, they actually see evidence for multiple stars close in the center that are affecting the ejecta from that star, that second star. And they think that this asymmetry is created by interactions with these multiple stars in this stellar system. So it's really amazing material. I'm going to now turn to our local solar neighborhood, because this is what I study. Here's a little map of our solar system, not to scale. The planets are usually not lined up like this in lines, and this is not the right orientation, but it's a map that I wanted to show you to remind you that JWST is right here. And remember, its sun shield is blocking the sun and the Earth, and it's also blocking Venus and Mercury. So there will never be JWST images of Earth. There will never be JWST images of Earth's moon, Mercury, or Venus. But everything else in the solar system is fair game. So that's the avoidance zone. But the team that I have is studying everything else. As an interdisciplinary scientist for JWST, part of my compensation for spending 20 years working on this project was 100 hours of guaranteed time. And I could use that time for anything that I wanted to do. The proposal I wrote to NASA was to use my guaranteed time to do a survey of JWST's capabilities within our solar system. And I could not do it alone. I have a very large team. These are the team leaders for each of the different aspects of the observations in my guaranteed time program. GTO stands for Guaranteed Time Observations. And if you just see the words, things like Mars, ocean worlds, that's Europa and Enceladus, Saturn's rings, giant planets, Titan, comets, Kuiper belt objects like Pluto, and near-Earth objects, near-Earth asteroids. These folks are the team leaders for all of that work. Each one of them has a team of about anywhere from 12 to 25 people helping to analyze that data. So it's a big effort, and I'm the chief cheerleader. I made this time available to all of these community members with the stipulation that the observations from my program had no proprietary time. As soon as the data is taken, it goes into our archive and it's available to every planetary astronomer in the world. That was my choice to do that. It's challenging because we don't have a lot of time to get our papers out because everybody in the world is jumping on our data right away. But that's the point. That was the point for me. I wanted my community members to have the data, not just the people on my team, but everyone. So let's talk about some of the things we found. Here's a beautiful Jupiter image from James Webb Space Telescope. You'll notice the beautiful red aurorae. Most of the auroral images that you see of Jupiter are taken in ultraviolet light with the Hubble Space Telescope. And you can see signatures of the auroral ovals. If you look carefully, that thin line is what glows in the ultraviolet in Hubble images. But this red stuff extending higher above the atmosphere, ionospheric glow from the aurorae in a line called H3+, that's like a triply ionized hydrogen line. It glows at the upper atmosphere, not only in the northern hemisphere, but all the way down in the southern hemisphere as well. You can see it extends far up above the cloud tops of Jupiter. One of the big surprises in Jupiter is if you look closely at the edge of the planet, you see what looks like a double line. You see a line there along the edge of the planet? This is the shadowed limb of Jupiter. Jupiter's edge is in shadow. So what is that line? We were all like, we don't know. Like, what is it? What could it be? Never been seen before, even though we've sent 2 orbiters, dozens of spacecraft doing flybys. This has never been detected before because we've never had an instrument so sensitive like JWST is that it could pull that faint glow out of the shadow. And what we, after a lot of debate, what we think that is that that glow that you saw up above at high altitudes, we believe that that glow is actually being distributed all around the planet. You can't see it most of the time because the planet is so much brighter. But here in the shadow, that thin, high ionospheric glow is visible to JWST. So our first JWST observations of Jupiter, we make a major discovery that had never been seen even with the spacecraft that are orbiting Jupiter. So I think that's why we still use telescopes and don't rely just on spacecraft, new things. Here's the great red spot. Some of you may be wondering, why isn't it red? The answer is this is not visible wavelengths. This is infrared wavelengths that we've transposed to visible so that you and I can look at them with our eyes. And the great red spot isn't red here, it's bright. It's bright because it just has a lot of clouds, and those clouds are scattering light back to us before it can be absorbed by methane in the atmosphere. And most of the around there is a lot, methane is absorbing the light, but there's a lot of high altitude clouds. And if you follow that logic, you'll say, well, gee, that equatorial region looks pretty bright too. You're right. There's a lot of hazy material in the equatorial region as well. And there's also these really tight, bright condensations you see through here, and then also up here. Looks like little worms even up there. What those are very, very high altitude thunder clouds, cumulus clouds that have punched through up to high altitude, and they're reflecting light just from those cloud tops. And they're just getting sheared out at those higher altitudes. And that's why they make these little distorted shapes. So lots of amazing science in this Jupiter image that the teams are working on right now to analyze and put numbers behind the numbers behind the highs and the lows, actual altitudes. That's the science that we do. I wanted to show you one more Jupiter image. And this is a single filter. So it doesn't have all those beautiful colors, although you can still see things. But the reason I wanted to show you this image is that you can see the ring system of Jupiter here. And a tiny Adrastea, that little moon's only about 200 kilometers across. And there it is right in these beautiful images. The rings, the brightness of the rings is about 1 million times fainter than the planet. And I hope that gives you a sense of the incredible dynamic range with JWST and the fact that we can image something 1 million times fainter next to this huge bright object. That's incredible. That's something that really only JWST can do at these infrared wavelengths. So great stuff. So here's a piece of an image, and I'm showing you this because it's pretty cool. Look at all those galaxies, right? All those dots, right? But if I zoom out so you can see the full image, you'll see something coming into the field of view there. And it looked a little bit like Saturn, didn't it? I mean, what is that? Let's zoom in here. Folks, that's not Saturn. That is Neptune. That's the planet Neptune. And that is Neptune's moon Triton. And Neptune looks fainter than Triton because at these infrared wavelengths, the methane in Neptune's atmosphere absorbs the light, makes it fainter. So let me zoom in on Neptune just so you can see it. And I'll share with you that when this image appeared on my computer screen, which is right here, big screen, you can't see it, but it's right next to me, I started to cry because this was the image that I joined this project more than 20 years ago to see. I had been working on the Voyager 2 spacecraft, studying Neptune. My thesis was studying Neptune with the best telescopes we had in the 1980s. And I wanted to help build the next generation telescope to see what Neptune looked like. So when this picture showed up, I was crying. And then I started yelling and jumping up and down and calling my mom in, and I called my kids in, and I held my cat up to the screen. They look, it's Neptune. It was just an amazing moment for me personally. And what I'm going to share with you is that this is just 4 exposures taken to make this particular picture by the Space Telescope Science Institute. This is not our Neptune science data. We haven't gotten our Neptune science data yet because the window to observe Neptune closed just after they got this picture, and it doesn't open again until the spring. So like April, May, we're like still a month or so away from getting our actual Neptune science data. So as joyful as this image has made me, it has only made me, excited for more. So stay tuned. There will be more Neptune data to come. We also looked at Mars. Mars is the brightest object that in the night sky that JWST will look at. It's very bright. This telescope is designed to see the faintest galaxies in the universe. And you guys, many of you are amateur astronomers. You know how bright Mars is. It's really bright. So it was hard to get an image of Mars that did not saturate. But we did this at our longer wavelengths. And so that's what you're seeing here is, sorry, I lost my cursor. Where'd it go? Here it is. You're seeing basically the heat from the surface of Mars that is in the sunlit side and getting cooler as you get away from the subsolar point. The Hellas Basin looks darker. And interestingly, that's not because it's cooler. It's actually darker because it's a basin. And so it's deeper and there's more atmosphere to look through there. And that high pressure of that thicker atmosphere actually changes the shape of the absorption lines at this wavelength and causes the absorption lines to broaden, which makes the light get fainter. And that's why it's darker. Complicated concept, but interesting science coming out of the JWST imaging. And of course, the JWST spectroscopy is really what we're all interested in because We are trying to study the overall chemistry of the atmosphere, not only like where the rover is, but from pole to pole and terminator to terminator, trying to limb, just get the overall concentration of atmospheric chemistry and how it changes with time. So that science is all in the works. You might have heard of the DART impact. This is what a mission that NASA had where they took a little mission, a little spacecraft, and they rammed it into the moon of an asteroid to try to change the orbit of that moon. And they did, they were successful. But it made a big explosion when it hit. And this movie that you're seeing here is a series of JWST images of that explosion. And it's really close into the nucleus. Most of the pictures you see in the background is a typical picture from a ground-based telescope where you can see this sort of explosion out here. The little red box is the JWST field of view. And so you can actually see, if you look closely, boulders flying off. You can see it tracking out there in this loop. And so the DART team is really interested in using these data to look at the details, the near details of the explosion. So it's pretty cool stuff. We were happy to support this. And we almost broke the telescope. The object here, Didymos, that we were tracking was 3 times faster than our upper limit of how fast we were supposed to track the telescope. But the amazing operations team for JWST managed to track the telescope fast enough for long enough to see this. The tracking failed after a little while, which is why you're only kind of seeing half a picture here. But they got us enough to be able to get some of these details. All right, let's talk about Saturn's moon Titan. The inset box here is our predictions before the spacecraft launched. And it's showing you the field of view of one of the instruments called the Near Spec IFU. This is the data that came from JWST. And so what you can see here, this moon, Titan, is encased in a thick smoggy atmosphere. And at infrared wavelengths, we can see through the smog down to the surface. We can see albedo markings on the surface. In this prediction, what you're seeing is a map from the Cassini spacecraft. And so you can see that we are picking up some of those albedo features. What's special, though, about JWST's IFU is that for every point here, we don't just have a brightness, we have the full spectrum, all of the wavelengths. And so we can measure the spectrum of this bright cloud and the spectrum of this bright region and the spectrum of the dark region and compare the different chemistries and the different temperatures and pressures in the atmosphere and on the surface from that spectroscopy. And so that is what is so powerful about these JWST observations of Titan. Now, this is a little object called Chiriclo. And Chiriclo is moving through the sky, and it went right past a star. And the star has a really long name. I don't remember the name of the star. It's a whole string of letters and numbers and things. But we had a program to watch the star as Chiriclo went past it. And the reason we were interested, first of all, you can figure out how big Chiriclo is, right? By watching how long it takes the starlight to wink out. But second of all, this little object, which is out in orbit beyond Saturn, like all the way out beyond Saturn, this little object has a ring system. It was discovered with a ground-based occultation. And so we had a prediction that we would observe the star blinking out as the rings crossed in front of it. We had hoped to see Chiriclo itself, but 3 days before these observations, the JWST did a standard course trajectory maneuver. It fired those little rockets. Remember, you saw them in the video. It fired those little rockets to put it back into a better orbit around L2. We do that roughly every 21 days. And this one happened just before this event. And that moved that dotted track off of the body, all right? So in our data, all we saw were the rings. So what you're seeing here is the star's light. And then when Chiriclo's first ring system comes along, it winks out. And then the star's back. and then the other side of the ring system, it winks out. And so this is how we can measure the size of the rings, the brightness of the rings, the optical depth of the rings. We'll compare this with other observations, other occultation observations of the rings, and learn if they are changing with time. Because how can a little body like Charikla, it's like a little, like an asteroid, how can it have a stable ring system? That doesn't even make sense, right? It doesn't have a mass have a ring system, and yet it does. There it is. You can detect it. We also pointed our spectrograph with JWST at that, and what you're seeing here is the spectral signature of crystalline water ice on the object itself. All right, this is the integrated light from the object and its rings. We hope to someday be able to separate the object and the ring system in our spectroscopy, just because we know the orientation of the rings is changing with time. So if we do more spectroscopy in the coming years, we might be able to tease out what light is coming from the rings and what's coming from the body. So that's just a taste. There's so much more I haven't talked about Enceladus, Europa. I haven't talked about comets or asteroids, Kuiper Belt objects, Pluto. All of these observations have been made. They're being analyzed by the team. If you have questions about them in the Q&A, I can get to that. But I had one more topic I wanted to talk about, and that is planets around other stars. Because remember how I said planetary systems and the origins of life? We weren't just talking about our planetary system. We're talking about planets around other stars. And the key way that we study them with Hubble and now with JWST is a technique called transits. And that's where this little body crosses in front of its host star, and we watch the starlight filter through the atmosphere of that planet. And we can see it in this, what we call a light curve. You can see how the starlight wakes out and then it comes back. And that characteristic dip is caused by the planet. And what we see when we do observations at different colors, different wavelengths of light, the depth of the dip is different. And so we can use that information about the light transmitted through the atmosphere to pull out the chemistry of the atmosphere. That's how we study the chemistry of planets around other stars. We take that variable dip in the light curve, we map it out as a function of wavelength, and then we get spectra. So here's a spectrum of an exoplanet atmosphere, and it's got a huge whopping emission line from carbon dioxide. This is something, of course, we have carbon dioxide in our atmosphere. We breathe out carbon dioxide. This doesn't mean that there are humans breathing carbon dioxide on this planet. WASP 39b is a hot Jupiter. It's a big giant planet really close in, but it is the first time that we had seen carbon dioxide in an exoplanet atmosphere. We're not as interested, I mean, there are people who love hot Jupiters, but kind of the holy grail for those of us who are studying planetary systems and the origins of life is not the hot Jupiters. We can't live on hot Jupiters. We're more interested in Earth-sized planets. And it's very hard to do this for Earth-sized planets around sun-like stars. So we tend to look at Earth-like planets around cool stars, M-dwarf stars. And this particular planetary system, the TRAPPIST-1 system, is a system of 7 moderately Earth-sized planets around a cool M-dwarf star. And 3 of those planets are at the right distance from that cool star that water could be liquid on their surfaces. And very intriguing. That's the kind of planet that we think may have life as we know it. Liquid water is required for life as we know it everywhere on Earth. And so we're looking in places where there could be liquid water. Now, I want to make clear, all those pictures you're seeing of those planets are just artists' concepts. Those are illustrations of an artist who was like, wow, I wonder what an Earth-like planet with oceans might look like. And they draw a picture like that, right? They made these beautiful pictures. In reality, we don't see these planets resolved like this. We just see points of light, or we see these transmission spectra. I want to ask the question though, even with the power of JWST, will we really be able to differentiate between the conditions on these worlds? Let's say those 3 worlds. What if we look at those 3 worlds and we see carbon dioxide on all three of those worlds. Here's 3 sample spectrum of 3 sample planets, and you see carbon dioxide in all of them. And in some of them, you see ozone and water. And these planets are actually Venus and Mars and the Earth. These are the planets in our solar system. This is what they look like in infrared light. And so just getting a low resolution spectrum that shows carbon dioxide on a TRAPPIST-1 planet, would it be a Venus planet or a Mars planet? If I see that, can we tell if that's what the exoplanet looks like? Is it Venus, where it's 900 degrees on the surface of the planet where lead melts? Or is it a dusty, barren, almost no atmosphere planet like Mars where humans couldn't live? Or is it a temperate planet like Earth? Just a low resolution spectrum may not be able to tell, all right? So there's going to be a lot of work that goes into interpreting these spectra. And there are thousands of planets out there. Don't get me wrong. There are at least 5,000. We've identified more than 5,000 planets around other stars in our local galactic neighborhood. So you might think, well, there's plenty of planets, right? Well, there actually aren't that many that we can study. How many can we actually do this work to do that spectroscopy and really tell if they have the conditions for life as we know it? And it depends on how big your telescope is. And so JWST is a pretty good sized telescope, a lot bigger than Hubble, but there's only tens of planets that we can characterize. And so over the next 20 years, as we're working with Hubble, you're going to hear the same names over and over again. You're going to hear all about TRAPPIST. You're going to hear about, there's other planets. There's another one that we're just talking about right now, whose name is escaping me in the moment. GJ 972 something B. We're doing studies of that one. They're hoping to find water. They haven't found the water. They're finding hints, but maybe not. But there's going to be like a few planets. So if we really wanted to answer the question, can we find a habitable planet with the characteristic signature, spectral signatures indicative of the potential for life? If we wanted to do it for hundreds of stars or even 50 stars, we need a big telescope. We need twice the size of JWST. And so remember the title of my talk, like what's to come? I'm merging into the what's to come section because, we do want to find life out there. We are at a moment in history, humanity, our species is at a moment in history where we know enough about our galactic neighborhood and we have powerful enough tools within our grasp to answer the question, can we find life on another world? And it's not going to be Hubble or Roman, another telescope we're building, or JWST. It's going to be something else. It's going to be bigger. NASA has tentatively calling this new next generation telescope, the Habitable Worlds Observatory. And honestly, we have the technology to build it. We have the people, the core, we call core competencies, means people who can do this. We have that to do it. And it will be capable of finding habitable worlds and maybe even life elsewhere. This is one mock-up of what it might look like. In the end, it probably won't look like this, but this is one of the concepts the teams have been toying with. I personally would like to see this launch by 2034. That's 11 years from now. It took us 20 years to build JWST. But this is not as hard as JWST because we don't need to do this in the infrared. To find these habitable worlds, we can look at visible wavelengths, and that's a lot easier than the infrared. And why did I personally pick that date? I picked that date because that's the 100th anniversary of the birth of Carl Sagan. And I knew Carl Sagan. I think he would be very excited about this idea that we are now on the cusp of building a tool that can answer the question, are we alone in the universe? It's really ambitious, but it's achievable. We're going to work, part of my job now is to work to see this new telescope come to be. So I wanted to sort of end this talk by trying to make the timescales a little human for you. So I'm going to turn on the Wayback Machine and go back to 2002. That's the year I wrote my proposal to NASA to become involved with this, James Webb Space Telescope. That wasn't what it was called then, but that's what I threw in. I wrote a proposal, and that's what I looked like in 2002. And that's my little baby Lucas. He was 1 in 2002, and that next picture is 2022, and that's my little baby Lucas, who is now taller than I am. So that's the year I wrote my proposal to get onto the JWST project, and that's the year we got our first data with JWST. So these are generational things to build these telescopes. That's a full generation. There are kids like Lucas. He doesn't do astronomy, he does art history, but there are kids his age who are starting to work with our JWST data, who are just babies, right? They weren't even born when we started to build this thing. So now let me ask, what is it going to be 20 years from now? I don't want to put a picture of me 20 years from now. I don't know what I'm going to look like, right? But we may still be getting JWST data 20 years from now. We have enough fuel to last 20 years. And that's because of that perfect launch from the Ariane 5. Before the launch, the fuel was our life-limiting factor. We were planning for a nominal 5-year mission, maybe 10 years that the fuel lasts, but we had so much extra fuel that we can now last for 20 years. The telescope may not last that long, but it's possible. But 2042, I want to see that other telescope flying, all right? So there's going to be other kids who are babies right now, maybe it's your kids, your grandkids, your neighbor's little kids. They're the ones who are going to use that telescope. So my final slide is just a quote from Carl Sagan, because I think it captures everything about JWST. For all our failings, despite our limitations and our fallibilities, we humans are capable of greatness. And to me, this JWST project that 20,000 people around the world all collaborated on for 20 years and is now up in space, sending back the deepest images of the universe we've ever seen, sending back new discoveries right in our local neighborhood, even on planets we had sent spacecraft to, and everything in between. That's what JWST is doing for us right now. And there's more to come, not only with JWST, but with this new Habitable Worlds Observatory that may help us find life in the universe. So thank you. I hope you enjoyed that. And now I'm happy to answer any questions that you may have about JWST. Let me unshare my screen. Stop sharing. Stop sharing. Now we're back.
Wow. Wow, thank you so much. That was really, wow, I really enjoyed that, your very passionate presentation, and we learned a lot, and it's really very inspiring. Thank you so much, Heidi.
You're welcome.
I still have to absorb what I heard so much. Thank you. Before we go into the Q&A, wait. Imelda, you have to unmute yourself.
Yes, Jen. We have some panelist questions. Particularly one panelist wants to ask, the first one to ask a question.
Well, this is a special panelist.
Are you able to get him, Jet?
I asked him to unmute.
Ah, it's David again.
Yeah.
David, you have to unmute. I'm muting you.
Heidi,
There.
I don't really have a question, much as I've paid close attention to your talk, your lecture tonight, and I've thought of questions, but I do have a comment instead. I have attended since the Zoom and other other similar features have been online. I've attended over 300 public lectures and scientific lectures, and a lot of them kind of mulch into noise and a lot of joy, but two of them absolutely stand out as outstanding, with a capital O, as my grandfather loved to say, and a capital G. The first one was Jocelyn Bell Burnell's lecture to the Astronomical League last summer. That was really something. And the second one was yours tonight. It was something. And I so wish that Wendy could be here tonight to have shared this with me. But if she were, I think she would want me to quote her favorite poem, which I will quote to you right now. It is Ralph Hodgson's The Song of Honor, the last few lines of it. And very often we would quote it together. I stood and stared. The sky was lit. The sky was stars all over it. I stood, I knew not why, without a wish, without a will. I stood upon that silent hill and stared into the sky until my eyes were blind with stars, and still I stared into the sky. So my question to you right now, which is more of a comment than a question, is congratulations on a magnificent lecture tonight. And I really hope that we're both around in 2042 to see the next space telescope and your lecture about it.
Thank you so much, David, for those kind words. I could hear Wendy saying those words with you. It's just wonderful. And I wish you were here too. You know, it's been a long road for all of us, hasn't it, over these decades? 30-something years since Shoemaker-Levy 9. And boy, oh boy, it's just fun to marvel at how far we've all come, how much we've learned, and then to think about how much there is yet to come. You know, there's so much more to learn. It's so exciting.
It was also so wonderful to see a picture of Lucas, as old as he is now, sharing my birthday. And I hope to meet him someday and to see you again someday.
I hope so too. That would be so delightful. We'll have to see if we can make that happen. So thanks so much for joining the lecture.
Thank you. It's my pleasure and my honor.
And I'll let you know, we do have a target of opportunity program for JWST, so that if we find another comet impact or asteroid impact takes place, if our amateur community finds one like they did in 2009, we have a program ready to go with JWST to do follow-up observations. So fingers crossed.
The other thing is the Canadians. The Canadians do not recognize the name James Webb Space Telescope. We Canadians call it the Just Wonderful Space Telescope.
I'm down with that. I like it.
Folks, just wanted to introduce David there. David Levy. Heidi, my apologies for not telling you. We wanted it to be a surprise. David wants it to be a surprise for you and to the rest of the viewers tonight. You know, we are so honored not just to have Heidi Hammel, but David Levy, the co-discoverer of Comet Shoemaker-Levy 9, whom Heidi interrupted during a press conference 29 years ago. So David wanted a payback and said, when Heidi gives her talk, I will interrupt.
Thanks, David.
Yeah, thank you so much. Thank you so much, David, for joining us again.
It's my honor and pleasure.
I would like to proceed now I would like to read some of the responses and questions from the audience. Here is one from our member, ALP member, Christopher Louis Lu. And he mentioned, thank you, Heidi, for the great presentation and ALP for organizing this. My question is, Do we expect to see deeper into Jupiter with the James Webb Space Telescope science instruments and more IR images of Jupiter?
Yeah, so JWST is probing the upper atmosphere of Jupiter, not so much the deeper atmosphere of Jupiter. We have a spacecraft orbiting Jupiter right now called the Juno spacecraft, and it has an instrument called a microwave radiometer, and that instrument actually probes deeper in the atmosphere. And then we have Hubble taking visible images. JWST's infrared sensitivity is actually somewhat in the higher part of the atmosphere, from the upper stratosphere into the ionosphere. And we actually are using all of the telescopes and spacecraft together to try to build up kind of a three-dimensional model of Jupiter's atmosphere. The program that in my guaranteed time specifically is focusing on Jupiter's Great Red Spot and trying to do a thermal mapping of the Great Red Spot to do sort of try to imagine some kind of a three-dimensional sculpture of the Great Red Spot from the top of the atmosphere all the way down deeper in the atmosphere. That's what we're trying to do with JWST. So there's going to be a lot of great science, and I also it's all about the spectroscopy. There's absolutely fabulous spectroscopy of Jupiter, different parts of Jupiter, bands and zones, and that is just like chemistry and dynamics and physics. So it's a hugely rich data set from JWST that the team has been working on now for a while. And I'm looking forward to seeing the products. They're not out yet, so stay tuned. We've released those images so you can see that we're getting the data, but the science is still, we're still pulling it all together. There's so much of it. We're all of us are like overwhelmed right now. My team is overwhelmed, every team. We're like a fire hose of amazing data, and we're just trying to get our hands around bits and pieces of it. So stay tuned, it'll all come.
Thank you, Heidi. There's a question related to that from Paul Anthony Cordova. Are there any volunteer research groups for JWST where we can volunteer to analyze data?
You mean like citizen science types of programs? Yeah,
Yes.
I think that some of the groups that are doing the large searches for many of these galaxies, they have citizen science components for them. My teams aren't doing that particularly, so I can't steer you to it, but I bet if you did some searching on with keywords like citizen science, JWST, galaxies, exoplanets, anything that's taking lots and lots of data that they have to sort through, they may have those opportunities. And I'll just mention too, we're building a new telescope called the Rubin telescope. It's a ground-based telescope in Chile. And there's going to be tons of citizen science opportunities with Rubin, because Rubin is going to be mapping the entire sky every 3 days for 10 years. And there's going to be so much changing. And so we need lots of citizen science working with it. So there's a lot of opportunities there.
Thank you, Heidi. I think this question came from one of our young watchers, Austin Diang. In order to, I'm sure with that lecture, Heidi, you inspired a lot of the young people now to go into astronomy and science. And the question is this one: in order to make discoveries, do research via the JWST, what will you have to study aside from math, physics, and computer science? Any specific areas of study needed?
Yeah, a good question. Now, of course, you're going to have to do your math. Math is really important. Physics is pretty important. Physics was never my strong suit. I will admit that right up front. That's why I majored in Earth and planetary science, but I had to learn a lot of physics, and I had to learn quantum mechanics because spectroscopy is all about quantum effects. So there's the science parts, but let me tell you a little story. During that Shoemaker-Levy 9 event that David and I were both part of back in 1994, it was a big deal, right? There was like a lot of news coverage and stuff. And my hometown in Pennsylvania sent a news crew to Baltimore to the Space Telescope Science Institute to interview me because I was like, local girl makes good, local girl running the giant big telescope. And they asked me that very question. They asked me, what was the most important course you took in high school to prepare you to be a world famous scientist? And I looked them straight in the eye and I said, chorus, my chorus class, singing. I had an absolutely outstanding teacher who had been a former Rockette and Radio City Music Hall, a dancer, performer on Broadway. And she was our teacher, and she demanded the top professionalism, anything she could get from us. You had to stand the right way. You had to breathe the right way. You had to sing the right way. You fidgeting, no nothing. She taught us to be professionals. She demanded it. And it was that level of focus that, really made an impact on me. And I brought that to my whole career. It's like, if you're going to do something, you want to do it right. Everything you do is right. And you work at it until you get it right. You aren't born knowing how to be an astronomer. You're not born knowing how to be a singer. You have to learn your craft. And so that's what that teacher taught me. And and I've talked to other successful people, and it's different for everyone. So it's really important in science to be able to communicate what you do, both verbally and in writing. So your writing classes are very important, and being involved in theater productions or singing or some kind of performance where you learn how to be a communicator. Those are just as important as your physics and your math classes. But the key is to whatever field you choose, to make sure you just do it the right way, do it the best, right? And it doesn't matter to me what it is. It doesn't have to be astronomy. It could be, it could be banking. It could be a hairdresser. It could be building bicycles. But whatever you choose, try to be your best at it. So good luck, whatever it is you decide to do.
Thank you, Heidi. The next question is from Alan Yu, one of our members. I agree with Mr. Levy. This is one really outstanding lecture. Though I need to lose some family time this morning, but never regretted every second listening to you. Thank you so much, Dr. Hammel. You made professional science look so cool again. I first saw you on TV way back in 1994 during the Shoemaker-Levy Levy 9 on a NASA press conference, and now I can never imagine the honor of hearing you in person. Truly a golden moment for any astronomers, amateur and professional. Thank you again. And then there's this question. Wait. Do you think the habitable worlds observatory concept can discover other mysteries of the universe other than searching Earth-like exoplanets?
Oh, yeah, absolutely. Yeah, for sure. Remember I talked about how JWST was designed to image the first galaxies in the universe. That's what its driving science goal was. But to do that, we had to build a telescope so powerful that we could use it to study galaxies and star formation and planets in our own solar system and planets around other stars. And the same will be true with the Habitable Worlds Observatory. The tool that we need, the machine that we need to be able to characterize dozens of Earth-like planets around sun-like stars, it's going to be so powerful that it will do revolutionary astrophysics as well as this goal of finding an Earth-like planet around a sun-like star that's habitable. So it's going to do lots and lots of other science as well. And that's another reason we want it to be a large transformational telescope, because, what the stuff we're doing now with JWST, this is the stuff that we've been planning for 20 years. Okay. Like, these are the questions we knew that we wanted to seek answers for. But what we're starting to find already, even though we haven't even finished one full year of science with JWST, we're starting to find things that are confusing us and challenging our models. Some of those earliest galaxies that we are seeing seem to be a little brighter or a little bigger than our current models suggest they should be. And we couldn't know that because we couldn't see them before. But now that we can see them, we're like, oh, wait a minute. Those models that we have, they're not matching these data. So we're going to learn something fundamentally new, right? And this is happening in like not only for the distant galaxies, but as I shared with you with Jupiter, we made a discovery on Jupiter, you know, big old Jupiter, that we currently have an orbiting spacecraft and had an orbiter in the past with Galileo and sent half a dozen or more spacecraft by Jupiter. And yet JWST takes a peek and boom, instant science.
Wow.
So in the next year or two, we're going to take these new discoveries that we're making and start to formulate new questions based on the new data. And we're going to go off in directions that even those of us who have been working in this program for 20 years haven't been able to imagine what question to ask because we didn't have the data to take us down that path. And now we do. So we're going to, I don't know what those young people are going to do with JWST. I mean, I know what I was going to do with it. I know my team did with it, but there's going to be young people and they're going to use it in ways that to answer questions that we didn't even know needed asking. That's really exciting.
Thank you. For the audience, please put your questions in the Q&A box in the Zoom app. So the next question is from Paul Anthony Cordova. Good day, ma'am. Can I ask about the JWST? What are the other current problems aside from fuel that have a threat to the telescope's viability?
Okay, that's a great question. So you may have already heard about micrometeoroid impacts. We knew that there would be micrometeoroid impacts because the big telescope is sitting out there in outer space with nothing protecting it. And so the engineering teams had done detailed models of what they believed the environment was like out at L2 and the micrometeoroid environment, and predictions about how often we would expect to be impacted on the mirrors by those. And we knew that there would be a size distribution. There'd be little impacts that wouldn't make any difference. There'd probably be occasional big impacts that would make a difference. And so there was a surprise to the team when in May, only a few months after launch, there was a pretty sizable impact on one of the mirrors, impact large enough to actually distort the shape of the mirror. And so it was readily detected in our data. It's like there's ways of studying those things with our data. And so people are like, oh, does that mean we don't really have it right? It turns out, though, there haven't been any large ones since then. There have been a variety of small ones. And when we look at the statistics of what we expected from micrometeoroid impacts, we did expect one of these kinds of pretty moderately damaging ones about once a year or so. And it just happened that once a year came early in the year and not later in the year. And that's just statistics. That doesn't mean that we're got lots of big ones. It just means the big one hit sooner rather than later. And so micrometeoroid impacts over the 10 or 15 or 20 years of the lifetime, they will degrade the quality of the images that we are getting. However, we had taken that into account from the very beginning. And so where we are set right now, the telescope, you may have heard this, and if I didn't say it, I'll say it now. This telescope is better in almost all of the specifications than we had expected, all right? In terms of its pristine quality, its sensitivities, everything is better, a little bit better than we expected. So the fact that we know with time, the quality will get worse and worse and worse, but we're starting at a better place. And so that's not going to be the life limiting factor, I don't think. But we talk about it. All electronics in space are exposed to a lot of cosmic rays. These are high energy particles that are flying through the universe. And if you just get one cosmic ray hit in a bad piece of your electronics, that can shut down your cameras, or it can distort your recording systems or your communication systems. So we do pay attention to those things. That's a possibility, an unfortunate cosmic ray strike into the electronics. Other possibilities, there are this is a very complex electronic system. There's a lot of bonds that are holding things together, but it's up in outer space at its very low temperature. And so there's just natural degradation of materials. And so we build into our timelines expected degradation, but sometimes things break. I mean, I don't know about you guys, but I got a car that's like really old, right? And just things wear out, right, over time. And so that happens with spacecraft too. And so there's just going to be wearing out of parts. So we don't really know what the one thing is that's going to do us in the end. Hubble right now is in fantastic shape, and its last servicing mission was 2009, right? It was like, and it's still doing great. And so NASA tends to do fabulous engineering. So I don't know what's going to be the end of this telescope, but I'm hoping it's not for a very, very, very long time yet.
Thank you, Heidi. So I will read another question here from Vincent Jelia, and I'll read another question, I think, which is related. With the JWST, just like to ask if you detected galaxies older than 13 billion years old. Thank you for this awesome lecture. And the next question is, in February, it was announced that JWST discovered a half dozen galaxies that formed between 500 million and 700 million years after the Big Bang that are more massive and more mature than expected. How does this finding impact existing theories about the evolution of galaxies and the age of the universe?
Okay, so your first one about how old the galaxies are, I don't have that memorized, but you can Google that information and pull it up. I'm pretty sure. I think that
older than 13 billion. I think the question was.
I think they're older than 13.
Yeah,
I think they're older than 13 billion. I think there's the one chart I showed. I think it was 13.1 and 13.3 and 13.8 billion years old. So they are older. And I remember I mentioned the very long surveys, the 20-hour surveys that are coming up. They will definitely get to very, very old galaxies. And that data isn't out yet. And so it's all being analyzed right now. So we have not yet broken all the records that we're going to break with JWST in terms of the oldest galaxies. You're just going to have to be patient and stay tuned for that. Sorry, what was the other question? Oh, wait, what was the second one again?
I'll read it again. It was announced that JWST discovered a half dozen galaxies that formed between 500 million.
Yeah, that's what I was talking about. These galaxies are more luminous and larger than we thought. And what the effect of that is going to be, back to the drawing table, those people who do models of the galaxies. It's like, okay, yeah, so you had these models, but they don't fit the data. So now you have to develop your models further. So it's gonna change our understanding for sure.
The next question is from an astrophotographer. Here's a question for Heidi. Is there any scientific feasibility to studying objects redshifted beyond the infrared? Is there any scientific feasibility to studying objects redshifted beyond the infrared?
So I have to think about that. That's more of a question for someone who studies galaxies. We do have some powerful telescopes already that are working at the longer wavelengths. After you go from mid-infrared and the long infrared, you go into really far infrared. And we've had space telescopes that do that. And we also have at that point, when they get long enough, you start using different tools, more like radio type telescopes. So we have a facility right now on the Earth called ALMA, the Atacama long millimeter array. I forget what the L stands for. Sorry, I'm having a senior moment here. ALMA is an array of telescopes that works at sub-millimeter wavelengths. All right, so those are not long wavelengths like radio. Radio, the wavelength of the radio beams is measured in feet and meters, but these are shorter, measured in millimeters and smaller than millimeters. And the ALMA telescope array down in Chile is making remarkable discoveries of mostly of protoplanetary disks. Not so much the distant galaxies. They're pretty faint. And there's a lot of interesting ideas we have for more powerful telescopes in the future. Right now, the Europeans are building an extremely large telescope. That'll be working, though, more at optical and near-infrared wavelengths. And the United States and partners are working on a 30-meter telescope and something called the Giant Magellan Telescope. Again, though, to your question about longer wavelengths, I'm not entirely sure what the real for those deep galaxies. I don't think that we have the sensitivity with our longer wavelength telescopes to pick them up yet. I think that's why JWST was built, because that's kind of where the peak sensitivity for those things is. But there's always more to learn.
Thank you. There's this question from Ira Joy Fernando. Thank you so much for the awesome lecture, Dr. Hammel. Your passion is really contagious. My question is, what would the detection of H3 plus in Jupiter entail? I think it's about triple ionized hydrogen, H3 plus in Jupiter. What does it entail? Its discovery, its detection.
Okay, I'm struggling a little bit with the word entail. I don't really know what that means. We look at spectroscopy, and we see emission lines from the H3 plus, right? And we know that the conditions required to make these emission lines require high energies, and they are the kind of energies you get when you have high energy particles in your magnetic fields impinging on your upper atmosphere of your planet. I mean, this is true not only on Jupiter and Saturn, but on Earth as well. Any planet with a magnetic field can trap and entrain high energy particles, and when they impinge on the atmosphere, they ionize the upper atmosphere, and that ionization is what gives rise to these emission lines that we see in our spectra. So we do spectroscopy. We also image at the precise wavelengths where we expect the emission to be. We take pictures at those wavelengths, and then we can compare it with pictures that are not at those wavelengths. And the difference between those two helps you spatially localize where these aurorae are happening. So it's a complex mixture of imaging and spectroscopy and the modeling of the magnetic fields and the upper atmosphere that gives us the understanding of what the H3 plus is doing and how it's tracing the auroral activity. I hope I answered your question somewhere in the midst of all that discussion.
I think so. Thank you, Heidi. This is a follow-up question from Austin Being. What is it like being an interdisciplinary scientist? What fields of science are you combining in your research?
Yeah, it's funny. It's kind of a misnomer, because the interdiscipline doesn't actually refer to the discipline of science that we do. In the case of JWST, what that interdisciplinary meant was that we scientists who were interdisciplinary scientists were permitted to use all of the instruments on JWST. In contrast, the other members who were working on the mission were working on specific instruments. There was the MIRI team building the MIRI instrument, and their science was designed for that one instrument. Similarly, the NIRSPEC team, the Near Infrared Spectroscopy instrument that was built by the European Space Agency, the team was using the NIRSPEC instrument to do their science. And there's 4 instruments on the telescope: MIRI, NIRCam, NIRSPEC, and then the NIRIS, which is part of the Fine Guidance Sensor from Canada. And so those 4 instruments had 4 teams, and those 4 teams used those 4 instruments. But there were 6 scientists selected for science, doing all the other science, and we were allowed to use all of the instruments. And of the 6 of us, they had people studying distant galaxies, people studying the formation of galaxies over time, people studying star formation and stellar evolution, and then the planetary systems and the origins of life. So our role was to be able to use all the instruments to advance our chosen fields. My personal chosen field was solar system observations, the local ones, but I could use all of the instruments, and my team does use all of the instruments. So that's what interdisciplinary meant in the JWST context.
Thank you. I would like to read, I think this is one of the first questions that was asked here from Tomas Encarnacion. Would JWST help in the hunt for the 9th planet? How? When?
So JWST is not the right kind of telescope to do planet hunting. JWST's got like a small field of view, but it's super precise in that small field of view. To find a planet that you don't know where it is, you don't want to be looking in tiny pieces of the sky. You want to look in large areas of the sky. So you really want a different kind of telescope to do the finding part. Rubin is an example. I mentioned the Vera-Rubin telescope. That's a wide field telescope. It might be a good finder. I briefly mentioned the Roman Space Telescope. This is a telescope that is like Hubble, but it has the Hubble sensitivity, but over a field of view 100 times larger than Hubble. And so it will be a finding kind of telescope. So the survey telescopes are the kind, there's another one called Euclid. The Europeans are building this Euclid survey telescope. There's some ground-based surveys right now, the Zwicky Transient Factory, the Catalina Sky Survey. There's a lot of surveys. They will be the telescopes that will find this planet if it exists. But once it is found, then we can point JWST at it and characterize it, because JWST is like incredibly powerful, but it won't find it. It's just not the right telescope for finding.
Thank you. So here's another question. If JWST can make detailed observations of the planets from its orbit, why does NASA still need to send unmanned space probes to explore those worlds? So,
well,
yeah.
Okay,
yeah.
sure. Like, you know what? There's a lot of things you can learn with fantastic telescopes, because that's what I do for my job. I'm doing that for 30 years now, right? But there are things you cannot do even with the most fantastic telescopes. Let me give you, I can give you a handful of examples. I'll only give you a few. One, you cannot measure the magnetic field of a planet remotely. Can't do it. You can look at the aurorae, and that'll give you some pieces of the clue of what's happening in the magnetic field, but you can't measure the magnetic field remotely. We don't have the tool to do it. And so you must have a spacecraft in orbit to be able to measure the magnetic field. Also, if you want to map out the interior structure, you need to have an orbiting spacecraft to give you the higher gravitational moments. You can't do that by looking at it from the outside. You get clues. Like you see, like Saturn is oblate, right? It's not a perfect sphere. It's kind of fat around the equator. And that gives you clues to the interior distribution of mass. But to really map it out, you must have an orbiting spacecraft. Also, if you want to study these ocean worlds, the geology and the geophysics of the ocean worlds, you can learn a lot from JWST. And we'll be publishing papers very soon about worlds like Europa and Enceladus. And, we've already got spectacular observations of these moons of Jupiter and Saturn. But moons of Uranus and moons of Neptune, like the amazing moon of Neptune, Triton, I showed you what it looked like in the JWST image. It's a blue dot. And what Voyager found when it flew past that blue dot in 1989 is that there are active cryovolcanoes erupting on Triton. You can't possibly observe those from the Earth or anywhere. The only way you could do it is with a spacecraft. which is why we want to send the spacecraft back to Neptune. So there's a lot you can do with telescopes. I mean, I've made my whole career using telescopes, but there's things you absolutely must be at the world or the moon or the ring system to actually study. So we work together. There's different ways of studying these objects, and you don't just want one or the other. They're complementary. That's why for the Cassini mission, it was studying the Saturn system, and one of the key complementary observations was the Hubble Space Telescope doing UV observations of Saturn's aurorae in conjunction with the Cassini spacecraft orbiting Saturn. There are different ways of doing this, multiple ways of studying the same system. So it isn't an either or. You need both.
Thank you. I would just like to read this comment question from an inspired watcher or one of our inspired audience. Good day, Dr. Hammel. Thank you very much for that amazing lecture. I couldn't help but feel emotional watching you talk about all these amazing discoveries that JWST has done and the colorful journey it came along with. My question is, what would you say to young women around the world to encourage them to study astronomy or inspire them to learn more? Thank you very much and happy Women's Month. From Stephanie Vergara.
Thank you so much for that question. You know, my goal is not to encourage young women to become astronomers. My goal is to encourage young women to pursue their passions, whatever those passions are. And I hope that, you know, I'm sharing my passion for the work that I do, the astronomy and the planetary science that I do. But I recognize that other people have other passions. And my hope, my wish, my dream is that young women have the ability to explore what it is that they love to do and that they can learn the things that they want to learn. There are many places on this earth where young women don't have those opportunities, and that saddens me. And so I try hard to show that women can do this work. When I started, it was a long time ago, I encountered people saying things like, I didn't know women could do that sort of thing. And I'm like, well, of course we can, you know. I just want people to have the opportunity to follow their passions wherever that takes them. So good luck to you and to all the young women watching this. Go for it.
Thank you.
Be brave.
Thank you. I think we're down to our last two questions. And this one is, I think, from maybe an interested scientist. How do observing projects get selected for JWST? How do observing projects get selected? Yeah.
That's a great question. It's open to anybody to propose. Once a year, there's a call for proposals to use JWST. And this is true for Hubble as well, and many of the large ground-based telescopes. And so scientists write proposals, but they do it anonymously. They say, they don't say, I'm Heidi Hammel, I'm a famous scientist, and I know what I'm going to use that telescope for. They actually have to anonymously write a science case saying, we want to solve this scientific problem. It requires JWST. And here's the problem, and here's how we want to use JWST to do it. And they never say who they are or where they are. It's anonymous. And then all of the proposals are all collected. This year for cycle 2, we just had a second year. The call for proposals brought in over 1,700 proposals from around the world. And they're all evaluated by panels of other scientists. They take all the solar system ones, they put them together, and they're reviewed by a team of solar system experts. And they rank them. And they say, this is amazing science, got to do. This science, you actually don't need JWST. So we're not going to do that. Use some other telescope. And then they argue about the stuff in between. And then they pick the top sector and they say, you know, congratulations, you have one telescope time. And the other ones is like, so sorry, we couldn't accommodate you, try again next year. And they provide feedback on, you know, the ones that are rejected saying, well, we rejected you because of this and that and the other. So the way it's done is it's a meritocracy. The best science is selected without knowing who those people are. Just how do we do the best science? And that's how we pick. And so it's a complicated review process, but we've been doing it for over 30 years with Hubble. That's how we decide who gets Hubble time. And that's how we're doing it with JWST as well. So if you have an idea that requires JWST, you can go online and figure out how the proposal process works. We just finished the first cycle, so you're going to have to wait for next year. But you can write a proposal, and if you do a good job, write a good justification, you could get time.
Yeah, I guess it's related to this question that was just added here. Can I add one more question? What can the Philippine astronomy community contribute to your research? I guess it's up to the Philippine astronomy community to do what you've just told us about the how to propose projects.
Right. That's right.
Yeah.
And I will share too. And I mean, my friend David is here. There's a very strong coordination between the amateur community and the professional community in many fields of astronomy. And I already mentioned the comet impact stuff. We're not looking at Jupiter 24/7 with JWST, right? We just aren't. We just have like little tiny snippets of time to do these things. But if the amateurs are looking and find interesting things and alert the professional community, that we can do follow-up work. That's what our target of opportunity proposals are all about. We have scheduled target of opportunity proposals where we say, we did this with Uranus too. I did this. I wrote a proposal for Hubble. This was a couple of years, many years ago, 10 years ago, 12 years ago, saying, if the amateur community is imaging the planet Uranus and sees bright cloud features, like really obvious, unusual bright cloud features that are verified independently by more than one amateur, we will trigger the Hubble Space Telescope to do follow-up observations of that bright cloud feature. And that was, we did that. We actually found some bright cloud features that the amateurs had alerted us to, that we could then say, hey, excuse us, we want to use Hubble. And we were able to because we had an approved program. And we do the same thing with JWST as well.
Thank you. The last question, I think, unless the panelists have other questions, but I think this could be the last question. And it's more of a personal one. And I think I already know the answer here. And I felt it already from your very awesome lecture and inspiring lecture. The question is, how does it feel to be able to use the world's largest and most expensive space telescope?
Well, it's amazing, I gotta say. I felt that way when I was using the Hubble Space Telescope. I really did. And I got to use that as a really young scientist. And that was a really humbling experience to be able to use a facility that was by far the best telescope in the world. And I didn't have anything to do with building the Hubble Space Telescope. It was other people built it, and yet I got to use it. And that's really kind of what inspired me to work for 20 years on JWST. Not so much for me, because I'd already done amazing things using Hubble, but I wanted to make sure the next generation of young scientists had that same moment where they could use this amazing facility. That was my dream 20 years ago. Just to set up this facility so that young people in my community could have that same feeling that I did of, wow, I can't believe I'm getting to use this incredible telescope. And, the young scientists on the program are making my dreams come true. The science they're doing is just amazing. And I'm just watching it going, yay, you go, you young men and women, you are doing the best. I just love it. And now we're going to try to do the same for the habitable worlds too, for the even younger generation, the ones coming up. We wanted to be there for them. We want to be able to continue our exploration of the universe. That's the goal. Keep it going. So thank you all for these amazing questions. I hope you've enjoyed the Q&A. I know I have.
Yeah. Do we have any last questions from our panelists?
Can I okay. Am I the first?
Yeah.
Go ahead, Peter.
Okay. Okay. All right. So yeah, I just have this is really a privilege to listen in to your talk, and I'm really thankful. I got to hear it from you, Dr. Heidi. So just a question that I had for years. Would you and JWST consider this project in searching for the heart of the universe? Is it possible at this point? The point is to prove if the universe is continuously expanding or if everything is revolving around a central object in different orbits that could explain why they are moving closer or farther from each other. It has been a question of thought, and I have asked this question to several expert speakers who have guested in our Astro Online talks.
Yeah, it's a challenging question that you're asking, because it's something that it's difficult for our human frame of reference to get our head around. When from our perspective here on Earth in our solar system, looking out into the cosmos, it looks like everything is moving away from us. But in fact, in the actual cosmos, everything is moving away from everything else. It's not that we're at the center, or there's not a center that everything is moving away from. Everything all the time is moving away from everything else. And this is something that's hard for us to conceptualize, because it's really not a three-dimensional problem. That, you know, it's not a three-dimensional thing. It's more of a four-dimensional thing. And it's a mathematical expression of how the universe is crafted that we can make observations of with our telescopes. But it's hard to conceptualize. And so we use analogies, and I'm sure people have told you these analogies before. We use the two-dimensional analogy of the surface of a balloon, just an absolutely uniform balloon that is expanding. And if you're an ant on the balloon, it looks like everything is moving away from you. But if you were an ant on the other side of the balloon, it would still look like everything's moving away from you. But then you transform that two-dimensional surface of the balloon into the three dimensions of space. And that's where, personally, my brain breaks down, because I don't understand that. But that is mathematically how that works. So I don't think that we're going to be looking for any center or heart of the universe, because our mathematical conceptions of the universe don't have that. It just doesn't exist in the mathematics. I hope that's helpful. There's a reason I study planets. I'm just going to say that, right?
All right. Thank you very much.
Imelda,
Yeah, I just want to add something to what Heidi said earlier, and I completely agree with her answer to that question about, you know, you got to find what you love and be good at it. Be very passionate at what you do and be good at it, because, you know, Heidi's using these fabulous telescopes, but truly there are a lot of people involved in, you know, not just designing, but building. You got to go to, you have a lot of engineers there who did their part, computer scientists and programmers who did the programs, the technicians. I mean, it involves a lot of fields, not just astronomy. So if you're good at computers, be a computer scientist, a computer engineer, a computer programmer. If you're good at materials, you know, you be a material engineer, or what's that field in engineering that does material stuff, or a mechanical engineer, or an electronic engineer,
Or teacher.
you know, or be a teacher, because you want to inspire the future generation. You're going to be the one that will mold the future generation of scientists and engineers out there.
You're exactly right. And 20,000 people brought their best. And it's not 20,000 astronomers. It's 20,000 people, exactly like you said, material scientists, electrical engineers, power specialists, spacecraft specialists, computer programmers, the artists and image processor specialists. All these people working together is what made a tool like JWST possible. And so I'm 100% behind, 110% behind what you just said, Imelda. Absolutely.
Thanks,
Thank
Heidi.
you so
Thank
much.
you so much.
Thank you, Heidi.
Heidi,
Yeah.
really, really appreciate what you did tonight. And can I announce to them that you maybe are, it's written now in pencil that next year's National Astronomy Week, we're going to have you.
Keynote
Next year.
Yeah, next year.
2024.
Yep.
Yeah. Thank you so much, Heidi. That's well, I don't have enough words to explain how I felt about that very inspiring lecture, and you explained everything in so much detail and so very clear. Well, maybe it's just like listening to Carl Sagan again with the enthusiasm. But let me take this opportunity now to present you our certificate of appreciation. And this certificate is presented to Heidi B. Hammel, Ph.D., for her invaluable insights, experiences, and expertise shared with the participants of the webinar entitled The First Year of the James Webb Space Telescope, What We've Learned and What's Still to Come, held as part of our ALP Astronomy Expert Speaker Series of 2023, given this 12th of March, signed by President James T. and Vice President Jose Francisco Aguilar. Thank you so much again, Heidi. And can we have a group picture with the other panelists? James, take the picture. David is still here. Hi, David.
James, you're still muted.
Hey, keep already get used to it. 1, 2, 3. One more. 1, 2, 3. Okay, got it.
Thank you. Thank you so much. And
Okay. Thank you,
Dr.
Heidi,
Hammel,
for accepting our
thank you so much.
invitation. Thank you very much.
Thank
Thank
you
you so
all.
much,
This was
Heidi.
Thank
wonderful.
you.
Thank you so much, Heidi. And thank you so much, David.
Thank you, David,
Thank you also, David,
Thank
for
you.
joining us.
for joining us.
Thank you all. Good night. Good morning.
Bye.
Good night.
By the
Bye.
way, you want to add something more? Yes?
No, we'll just close the program. I'll
Okay.
make the closing remarks. Thank you so much.
Okay, thank you.
Bye.
Thank you.
All right,
Bye-bye.
thank you. Thank you, everyone.
So that was great, really. And before we conclude today's fantastic webinar, I would like to thank all our attendees for joining us. We will be sending you certificates of attendance for today's webinar by email to all registrants who were able to join us today. This is the third talk for our 2023 Astronomy Expert Speaker Series last year we had 10 speakers for our webinar series. Our past webinars have all been recorded and could be viewed at our ALP YouTube channel shown in our ALP YouTube channel, and you can just search for it. So we are very grateful to all our past webinars who very generously gave their precious time to share their knowledge and expertise to the world amateur astronomical community. And we can never thank you enough. And just to announce, for the next month, we will be celebrating Global Astronomy Month. And this will be on April 15, 2023, that's Saturday at 8:00 p.m. The ALP will be hosting 2 online talks by 2 of our ALP members. The first talk will be given by Mr. Raymond Sarmiento, who will discuss the amazing EQMOD story, how it came to be and how it is helping amateur astronomers and astrophotographers worldwide. Our other speaker will be none other than our very own Mr. Enrico Africa, who will share experience about remote observatories and hopefully help other amateur astronomers and astrophotographers start or experience their own remote observatories. And also on April 30, we will be also having on that month, we will be also conducting ALP public stargazing activities, April 16, 22, and 29. Please wait for further announcements. Also for the talks we will be posting at our website at https://astroleaguefields.org. And just please wait for it, and we will be posting it as soon as possible. And on April 30 also, next month, Sunday morning, 9:30 a.m., as part of our ALP Astronomy Expert Speaker Series, we will be having Dr. Daniel Green of CBAT to give a brief tutorial on comets. So we will have 3 online talks on April. And on May 30, also as part of our ALP Astronomy Expert Speaker Series, the president of the International Astronomical Union, none other than Dr. Deborah Elmegren, who was our guest during our last webinars, will talk on her work, A Glimpse of Galaxies at the Dawn of the Universe. This will be on May 20, Saturday, 8:30 p.m. Philippine Standard Time. Again, we will be making announcements in our webpage and in our social media page. Thank you so much, everyone, and clear and dark skies. And for the panelists, I will be posting the link for our post-webinar Zoom meeting after this. Thank you. Bye-bye.
Right.